All right, we're moving into a brand new section now, acid-base titration. These three objectives are what we're building toward. First, you'll learn to predict what actually forms when acids and bases react together. Second, we're zooming in on a critical moment called the equivalence point. That's when you've added just enough titrant to completely neutralize the analyte, and the solution has special properties we need to understand. Third, and most practical, you'll use real experimental data from titrations to work backward and find out how concentrated an unknown acid or base actually is. This is real lab chemistry. These are your success criteria, the concrete skills you'll master in this section. The first two build on what we just covered, writing balanced neutralization equations and truly understanding what the equivalence point means physically. The third is your practical tool, the dilution equation CAV equals CBVB. This golden equation lets you solve for any unknown concentration when you know the volumes and one concentration. It comes straight from the fact that at equivalence, moles of acid equals moles of base. That's why it works every single time. Now we're moving into titrations, the experimental technique where you actually use those calculations we just learned. A titration is the controlled addition of a solution of known concentration to another solution until the reaction is complete. Think of it as the hands-on application of everything about equivalence points and the dilution equation. You'll learn how to perform a titration in the lab, recognize when you've reached the endpoint, and use your measurements to calculate unknown concentrations. This section bridges theory and practice. So here's the key insight. A titration is fundamentally about using a neutralization reaction to find out what you don't know. You take a solution where you know both the concentration and the volume. That's your standard. You slowly add it to an unknown solution until the reaction finishes completely. By measuring how much of your known solution you used, you can calculate the unknown concentration. It's like a balance scale. If you know one side perfectly, you can figure out what the other side must be. The beauty is that the math all comes from that stoichiometry of the acid-base reaction and the mole relationship at the equivalence point. Now let's talk about the equivalence point. This is the exact moment when your titration is complete. It's when you've added just enough standard solution so that the moles of acid and base are perfectly balanced, chemically speaking. Notice the example. 0.15 moles of NaOH neutralizes 0.15 moles of HCl, but it takes 0.30 moles of HCl to neutralize only 0.15 moles of BaOH2, because that base has two hydroxide ions. You detect this point using an indicator dye that changes color right at the equivalence point's pH. For strong acid-strong base reactions, that's around pH 7. Here, we're defining two essential vocabulary terms you'll use constantly in titration work. The endpoint is what you actually observe, that color change in your indicator dye. It's your visual cue that the reaction is done. Ideally, this happens right at the equivalence point we discussed, meaning the indicator's color change pH matches where all the moles finally balance. The standard solution is the reagent with a precisely known concentration that you're adding from the burette. This known value is crucial because it lets you calculate backward to find the concentration of your unknown sample. Now let's look at the actual procedure for a titration. You're adding a standard base of known concentration dropwise into your acid sample of unknown concentration. Think of it like slowly filling a cup. You keep adding until you hit that endpoint we discussed, when the indicator changes color. The apparatus shows you the burette where the base comes from, the stopcock to control the flow, and the flask holding your unknown acid. You're essentially using the math concept of moles to figure out what you don't know by using what you do know. Your textbook has the complete step-by-step procedure on page 490 for the full details. Now we're looking at titration curves, the visual story of what happens as you add base to acid. The curve shows pH on the y-axis and volume of titrant added on the x-axis. Here's the key insight. The equivalence point is where that dramatic vertical jump occurs. Notice the half equivalence point at pH 4.75, where pH equals pKa. This is where the buffer capacity is strongest. That steep vertical section, that's where the indicator changes color. The curve starts relatively flat because the acid is buffering, then suddenly shoots up once all the acid is neutralized. This shape tells us exactly when we've reached complete neutralization. This curve shows what happens when you titrate a strong acid with a strong base. Both completely dissociate, so the chemistry is straightforward. Notice the equivalence point sits at pH 7, not pH 4.75 like with a weak acid. Why? Because when a strong acid fully neutralizes, you get just salt and water, no buffer forms. The vertical jump is even more dramatic here because there's no buffering capacity to resist pH changes. Before equivalence, the pH stays very low because excess strong acid dominates. After equivalence, excess strong base shoots the pH up rapidly. The color change happens right at that vertical section where the indicator's range catches the steep rise. Now we're switching gears to titrate a weak acid with a strong base. See how this curve looks different? The equivalence point shifts to pH 9, not 7, because the conjugate base left behind is weakly basic. Before equivalence, you have a buffer, the weak acid and its conjugate base together, so the pH rises gradually instead of staying flat. The vertical jump at equivalence is less dramatic than strong acid, strong base, because that buffer resists pH change. After equivalence, excess strong base dominates and pH climbs steeply. This is why weak acid titrations are more interesting. Buffering creates that S-shaped curve we see here. Now it's your turn to read the graph. Look at the titration curve on the right and find where the steepest vertical section occurs. That's your equivalence point. Read straight across to the pH axis and tell me what value you find. This is a weak acid strong base titration, so remember the equivalence point won't be at pH 7. Use the grid lines to help you identify the exact pH. What do you see? Perfect. You found pH 5 at the equivalence point. This confirms what we said about weak acid strong base titrations. The equivalence point is definitely above pH 7. Here's why. When the weak acid is completely neutralized, you're left with its conjugate base in solution. That conjugate base hydrolyzes, accepting protons from water and producing hydroxide ions, which shifts the pH into the basic range. The degree of hydrolysis determines exactly how high, in this case, it brought us to pH 5. This is fundamentally different from a strong acid strong base titration, where equivalence would be at pH 7. Now we're moving from understanding what happens at the equivalence point to actually calculating unknown concentrations. The key insight is that at equivalence, moles of acid equal moles of base. They've completely neutralized each other. So we can rearrange the molarity equation, M times L equals moles, to compare the two solutions. This formula, C in Vn equals C2V2, lets you solve for whichever unknown you have. As long as you use matching volume units on both sides, both milliliters or both liters, the math works perfectly. This is your workhorse equation for titration problems. Now let's apply the C in Vn equals C2V2 formula to a real problem. We have rubidium hydroxide being titrated with hydrobromic acid. Notice we're given the acid's molarity in both volumes. We need to find the base's molarity. Watch how we rearrange, solve for the unknown concentration by dividing the acid side by the base's volume. Plug in the numbers carefully, keeping milliliters on both sides so they cancel. The arithmetic gives us 0.7819 molar. That's our answer. This is the exact process you'll repeat for every titration problem. Now it's your turn to solve a titration problem independently. You have 30.0 milliliters of sodium hydroxide at 5.00 times 10 to the negative 3 molar that neutralizes 11.5 milliliters of an unknown hydrochloric acid. Your job is to find the acid's molarity. Use the C in V1 equals C2V2 formula we just practiced. Identify which concentration and volume belong to the base and which to the acid, then rearrange to solve for the unknown. Remember to keep your units consistent. Milliliters will cancel when you set it up correctly. Try working through this one on your own first, then we'll go through the solution together. Here's the complete solution to your titration problem. We rearranged the dilution formula to solve for the acid's molarity, which is the unknown. Notice how the milliliters canceled out perfectly. 30.0 divided by 11.5 equals about 2.6, and when we multiply that by our base molarity, we get 0.0130 m. This means the HCl solution is more concentrated than the NaOH because it needed less volume to neutralize the same number of moles. The answer tells us acid strength isn't about volume, it's about concentration.